And now with the fresh air it's fine. But I just put my sweater on because I have a cold and I have to just be a little bit careful, otherwise I lose my voice and I have to teach also tomorrow with the Okay, and so basically I can write now EB is equal to 1/8 GHB squared. Good. But this is not the energy flux yet. This is the energy of the wave per unit area. Okay, and I'm not sure, it goes here. I'm not sure, okay. There is, of course, there are other ways of computing it. And there is, I think, a simpler way of computing it, which is reported in my web page. And let's see the simpler way. So, basically, I can consider that the kinetic energy is null when the wave reaches the crest. And also when it reaches the through. And therefore, I can compute simply the potential energy at the wave crest without taking any average and assuming that is equal to the total wave energy. In fact, what you see up there is just the same computation. What it changes is the fact that it refers already to the total energy and it refers to the wave crest. So you see that the integral is extended by minus dB, like before, to the wave crest. HB half is the wave crest. HB is wave height. So HB half is the coordinate of the wave crest with respect to mean sea level. Okay, good. So this is the integral. Again, I have to subtract the integral between minus dB and 0 because I want to get the energy of the wave with respect to the sea surface. And therefore, I get the same result, meaning that it's 1/2 already expresses in terms of HB. 1/2 rho G HB half squared, which is equal to 1/8 rho G HB squared. It's the same thing. This is simpler. It's simpler, but you know, it's interesting to see both of them. Okay. Now, again, this is potential energy with respect, total energy for unit area. Now, what I want to compute actually, it's the energy at the breaker line. And I'm not really interested in energy per unit area. What I'm interested in is, if I imagine to stay on the breaker line, I am on the top of the wave, over the breaker line. The breaker line, you understand what it is. It's the line, we're talking about a plane wave, and therefore it's the line where the wave breaks. It breaks at the same time along the transversal direction. So if the wave is moving like that, the fact that it's a plane wave means that it cannot break in that position before that in that position. It's a breaker line. Okay, so I'm standing over the wave at the breaker line. What I'm interested in is the flux of energy per unit time that the wave transmits per unit width to the beach. So this is what I'm interested in. So, given that I start from an energy per unit area, at this stage, I have to introduce the wave velocity to get energy over time per unit width of the wave. So basically, if I know the energy per unit area, if I put the velocity in, only one spatial dimension remains left, which is the unit width. So basically, again, I start from energy per unit area. If I multiply this energy times the velocity, it means longitudinal direction over time. The energy becomes an energy per unit width. Is the only dimension I did not multiply the energy by, and per unit time, because it's velocity. So velocity is dimension in the longitudinal direction divided by time. So energy per unit area multiplied by longitudinal direction per unit time, it remains energy per transversal direction per time. So this is why I multiply EB times the velocity of the wave. Here it's called the group velocity, because this is more generic. Maybe in the group velocity we talk about velocity of the wave with a single plane wave. When we have several waves interacting, we talk about group velocity. So this is more generic, group velocity. If you are talking about a single wave, you could just say velocity of the wave. Okay, and therefore you obtain what I just said, the wave energy flux through a vertical plane of unit width perpendicular to the wave direction. The plane where I am standing over. And this is the energy flux, and we assume that this energy flux is related, is proportional to the flux of segments. Don't be too much concerned. Now I think it's time that we stop for 10 minutes and take a coffee. Okay? I wanted to make also another slide, but the fact that you breathed it is so convinced me to stop now. Okay.
The last part that you say is the energy flux is proportional to
the flux of segments.
Flux of segments.
Yeah. And I should have said flux of weight of segment. Okay.